Welcome to today's episode, where we explore the role of gravity in space travel. Gravity, a fundamental force of nature, plays a crucial role in the mechanics and challenges of traveling through space. Join us as we delve into how gravity influences everything from rocket launches to orbital mechanics and interplanetary travel. To understand the role of gravity in space travel, let's start with the basics. Gravity is the force that attracts two bodies towards each other. On Earth, it gives weight to physical objects and causes them to fall towards the ground when dropped. In space travel, gravity is both a friend and a foe. It is the force that keeps planets, moons, and satellites in orbit. But it also poses significant challenges for launching spacecraft and maintaining stable trajectories. When a rocket is launched, it must overcome the gravitational pull of the Earth. This requires a tremendous amount of energy. The speed needed to break free from Earth's gravity, known as escape velocity, is about 11.2 kilometers per second. Once in space, gravity still plays a key role. In orbit, a spacecraft is in a state of continuous free fall towards the Earth. But because it is moving forward at a high speed, it keeps missing the Earth, creating what we call an orbit. Orbital mechanics, the study of the motion of objects in space, is heavily influenced by gravity. The paths that spacecraft take around planets and moons are determined by the gravitational forces exerted by these celestial bodies. Let's consider the International Space Station, or ISS. It orbits the Earth at an altitude of about 400 kilometers. At this height, Earth's gravity is still strong. But the ISS stays in orbit because it moves forward at about 28,000 kilometers per hour. Gravity assists, or gravitational slingshots, are techniques used by space missions to gain speed without using additional fuel. By passing close to a planet, a spacecraft can use the planet's gravity to increase its velocity and change its trajectory. One famous example of a gravity assist is the Voyager missions. Both Voyager 1 and Voyager 2 used the gravity of planets like Jupiter and Saturn to accelerate and change course, allowing them to travel further into the outer solar system and beyond. Interplanetary travel also relies on precise calculations of gravity. To send a spacecraft from Earth to Mars, scientists must account for the gravitational pull of both planets and plot a trajectory that allows the spacecraft to arrive at the right place and time. Gravity not only affects the motion of spacecraft, but also has significant implications for the health of astronauts. Prolonged exposure to microgravity, as experienced on the ISS, can lead to muscle atrophy and bone density loss. To mitigate these effects, astronauts follow strict exercise regimens and use specialized equipment to simulate the effects of gravity on their bodies. Research is ongoing to better understand and counteract these health challenges. Future space missions, such as those aiming to establish bases on the Moon or Mars, will need to address the challenges posed by different gravitational environments. The Moon has about 1/6 of Earth's gravity, while Mars has about 1/3. Artificial gravity, created by rotating spacecraft or habitats, is one potential solution to provide a gravity-like environment for long-duration space missions. This concept, while still in the experimental phase, could help maintain astronaut health on missions to Mars and beyond. Gravity is a fundamental force that profoundly influences space travel. From launching rockets to maintaining orbits and ensuring the well-being of astronauts, understanding and harnessing gravity is essential for the future of space exploration. As we continue to explore the cosmos, our knowledge of gravity and its effects will enable us to venture further and accomplish more. Thank you for joining us on this journey through the role of gravity in space travel. Let's delve deeper into the intricacies of gravity and how scientists and engineers work with this powerful force. One critical aspect is the use of gravity wells, which are conceptual models used to understand the gravitational field around a planet or star. A gravity well illustrates how much energy is needed to move an object away from a celestial body. The deeper the well, the more energy is required. For example, Earth has a deep gravity well compared to the Moon, meaning more energy is needed to launch from Earth than from the Moon. Gravity also affects time, a phenomenon known as gravitational time dilation. According to Einstein's theory of general relativity, time moves slower in stronger gravitational fields. This effect, although minuscule on Earth, becomes more significant near massive objects like black holes. This time dilation must be considered in space travel. especially for missions involving high speeds and strong gravitational fields. For instance, GPS satellites must account for the differences in time caused by the Earth's gravity to provide accurate positioning data. Moreover, understanding gravity is crucial for landing on other planets. The descent and landing phases of missions like the Mars rovers are carefully planned to account for the planet's gravity, ensuring a safe touchdown. Gravity also impacts the design of spacecraft. Engineers must consider gravitational forces when planning the structure and materials of spacecraft to ensure they can withstand the stresses of launch and travel. In deep space exploration, gravity assists become even more critical. Missions to the outer planets or beyond the solar system rely on precise gravitational calculations to navigate the vast distances and conserve fuel. The study of gravity extends to future technologies, such as the concept of a space elevator. This theoretical structure would use a cable extending from Earth's surface to a point in geostationary orbit, utilizing the balance of gravitational and centrifugal forces. While a space elevator is still in the realm of science fiction, ongoing research into materials like carbon nanotubes brings us closer to making such concepts a reality, potentially revolutionizing space travel by reducing launch costs and increasing accessibility. Additionally, gravity plays a role in the potential for colonizing other planets. The lower gravity on Mars, for instance, presents unique challenges and opportunities for human settlement. From the impact on human physiology to the design of habitats and infrastructure, understanding and adapting to different gravitational environments will be key to successful long-term missions and the establishment of human presence beyond Earth. This includes developing technologies and strategies to mitigate the health effects of reduced gravity. In space stations or habitats, artificial gravity could be generated through rotation, creating a centrifugal force that simulates gravity. This could help maintain the health and well-being of astronauts on extended missions. As we look to the future, mastering the role of gravity in space travel will be essential for exploring new frontiers. From establishing lunar bases to sending humans to Mars and beyond, gravity, with all its challenges and opportunities, remains a fundamental aspect of our journey into the cosmos. Thank you for joining us in this exploration of the role of gravity in space travel. Stay tuned for more insights into the wonders of space exploration.